All right, welcome Honors Pre-Calculus. This is a lesson on Unit 4, Topic 1, the algebra of vectors, and it's our third lesson in 2021. We're going to look at the dot product and the angle between two vectors. So if you would go ahead and start with this warm-up. We've got two puppies, Arlo and Buster, pulling on a rope in opposite directions to see the image. Arlo is pulling directly west or left with a force of 1 Newton. Buster is pulling directly east or right with a force of 1 Newton as well. So what do you think will happen to the rope? Go ahead and pause the video and give it some thought. All right, I'm assuming you've paused the video and tried the problem. What we're doing today is the second to last day of vectors. We have dot product and angle between two vectors, just because this is a pre-recorded lesson. So I guess I can do as much as I want on the pre-recorded lesson. So let's do both. We have our warm-up, we'll do some definitions and frame the learning, and then transition to guided practice, a little bit of discovery, and we'll close with our check for understanding. If we have time, I'll give you some time to workshop and work on homework. And that's it. And then my in-person folks, you all are doing hopefully some breakout rooms. So looking forward to seeing how that goes. We've got homework informative as always, and it's useful for you to have your Zoom, your Nearpod, and your scientific calculator in degree mode. Okay. So what is dot product? This is the main piece of our learning today. So the dot product, this is the formula that's in your formula sheet, right? Vector U is composed of your X component and your Y component. They're calling that U1 and U2. Vector V is composed of also an X and Y component. They're calling that V1 and V2. So the dot product of vector V and vector U are the X components multiplied together, U1 times U2, plus the Y components multiplied together, U2, V2. So U1, V1, I feel like I just said it wrong. U1, V1 plus U2, V2. So this is just an illustration of what comes into play when you're talking about dot product versus cross product. We're not really going to do cross product this year, but dot product is really involving the components that are going along the same axis. So AX, BX, AY, and BY. And then if you had a three-dimensional vector, AZ, BZ. All right, so let me explain what it is, what dot product is. So piece by piece, we're just explaining it. And this is an image from betterexplained.com that has a really good video on it. If you want to watch that later and you want more examples of how this is going to make a little bit more sense. So if you think about the dot product as like a piece by piece, right? What does it mean to multiply the X components and multiply the Y components and add them together? So what the dot product is really measuring is the force of one vector on another in the same direction. So how do the X components interact and how do the Y components interact? So say you have this vector A and vector B. The A vector is red, the B vector is blue. We talked last week about how you break the vector down into its components. So your X component is magnitude cosine of theta, your Y component is magnitude sine of theta, right? So any vector you can break down into like a right triangle with legs and calculate the components, just like we did last week. Okay. So what dot product is kind of doing is kind of like foiling the vectors, right? So the X components multiplied together, the Y and the X and the Y, and then the Y's. Like you're basically taking each piece of the vector and multiplying it with the other piece of the other vector. So each vector component gets multiplied by each vector component of the other vector. Okay, so when we have AX times BX, that's going to be whatever, this direction is times this direction, plus AY times BX, which is going to be 0. Because perpendicular vectors, right, their Y components don't affect the X components, and their X components don't affect the Y components. It's really just, it's 0 for both of the sort of the crosses, the AY and BX and the AX BY. And then you multiply the AY BY, so we multiply the two vertical components together, and then that is the result of your dot product. And we're going to talk a lot more today about what this perpendicular vector relationship means. Okay, so that's kind of what a dot product is broken down. Why is it useful to know? So with solar panels, for example, solar panels, the angle that the sun is hitting on a solar panel really, it does affect the solar panel's effectiveness, right? You want that direct sunlight as much as you can. So you want that energy, those vectors lined up. So the way the solar panels are built on their roof are designed to receive as much sunlight as possible. And the better your sun angle is, the better the alignment for the solar panel vectors will be. Okay, another probably more close to home example is if you play Mario Kart, whenever you go over a speed boost pad in Mario Kart, you really want to hit it straight on so that your vector components are lined up, and that gives you the biggest speed boost, right? So when whoever character you like to play a Mario Kart, if you're going straight through that speed boost, right, lining up in the perfect direction with the speed boost, you get the most speed. So that blue vector is showing the direction and that you want to go in. Here you see that this character is not quite doing that, right? This character is coming at it at an angle. It's not going to give, looks like it's not going to give as much bang for the buck. Okay. Okay, so here's the formula, just like we had it earlier in your formula sheet. I just wanted to show this to you so that you could see what the formula sheet looks like and how it's going to appear whenever you look at your formula sheet for this class. This is the way MCPS has set the dot product of two vectors in the plane formula up. So the way you can think about it is that it's the product of the x components plus the product of the y components. So U1, V1 is just your x components of both vectors, U2, V2 is your y components of both vectors. Okay, so let's get into dot product and revisit Arlo and Buster, the puppies from the warm-up. So whatever you said in your warm-up, I want you to kind of connect back to now. So you've got Arlo pulling west and Buster pulling east, and they're both pulling, they have the same magnitude. Their dot product, if you multiply the x's and then multiply the y's and add those together, is -1. And that means that the projection of Arlo's force onto Buster's force in the x direction is -1, which makes sense because they're pulling in opposite directions, right? So the way you compare Buster's force to Arlo's force is it's -1. It's the complete opposite of the other puppy's force. Okay, so there's no vertical comparison, right? Because it's just 0 times 0, but horizontally, they're each exerting an opposite force from the other one. Okay. So now I want to change it up a little bit. So let's say that they're pulling, now Arlo's pulling east and Buster's pulling north. So now imagine that both puppies are pulling the rope in the direction of the vectors on the graph, right? So Buster has his vector is 0, 2, Arlo's vector is 2, 0. I want you to try to calculate their dot product. You have the formula up here, and then tell me, what do you think their dot product is telling us? What do you think it's telling us? So go ahead and give that a try. Pause the video. Okay, I'm assuming that at this point you have paused the video and tried the problem. And let's review. So Arlo's x component times Buster's x component plus Arlo's y component times Buster's y component. So 2 times 0 plus 0 times 2. So that equals 0. Okay, interesting. So what this means is the projection of Arlo's force onto Buster's force in this case is 0. The x components are not cooperating. Arlo is totally on his own to pull east, right? And the y components aren't really cooperating. Buster is on his own to pull north. So they're not interacting with each other. These vectors are perpendicular. Buster is totally responsible for the y direction. Arlo is totally responsible for the x direction. They're not interacting. Okay. All right. So now that we kind of have a sense of what this means and what the meaning of dot product is and what it's actually measuring, right, which is the projection of one vector onto the other vector, let's practice calculating it and make some meaning of it. So on the next slide, you have 3 sets of 2 vectors, and I'd like you to calculate the dot products of each vector. If you notice a pattern, go ahead and state what you think it is. All right, so go ahead and practice. Pause the video and try these 3 dot products. Okay, I'm assuming you've had a chance to practice. Let's review. So our first dot product was 5. 2 times -2 is -4. 3 times 3 is 9. So -4 plus 9 is 5. So this dot product is 5. So the force that each of these vectors are exert, or the projection of these vectors onto the other, is 5. All right. The second pair is 0. 2 times -3 plus 3 times 2. That's -6 plus 6 is 0. And then the last set of vectors is also 0. Okay, and I'm not sure what you said because this is just a recorded video, but when vectors are perpendicular or orthogonal at right angles to each other, their dot product is 0. Their dot product is 0. So that's a big takeaway from today. When you have perpendicular vectors or orthogonal vectors, they're at 90-degree angles to each other, their dot product is going to be 0. All right. So just a quick recap of that. So if the dot product of two vectors is equal to 0, the zeros are orthogonal or perpendicular to one another. And then the converse is also true, that if vectors are orthogonal to each other, their dot product is 0. Okay. Another thing that doesn't require quite as much work, but I do want you to know this, is that you can also determine if vectors are parallel. So if two vectors are scalar multiples of one another, they are parallel. Or you could think about it if ax times by equals bx times ay, and then the converse is also true. And the reason I'm not spending as much time on parallel vectors is that it's very similar to your algebra 1 idea of the slopes being the same. So you see these two vectors, they are parallel. You can see that the change in y over the change in x are the same for both vectors. So the idea of them being a scalar multiple to each other is just that, right? This vector goes in the direction, it goes, left 3 and up 1. So does this vector, right? 2 to -1 is left 3, 3 to 4 in the y direction is up 1. Okay, so parallel vectors are a little bit more of a straightforward concept. That we spend more time on the orthogonal idea because it's related to the dot product, which you just learned about 10 minutes ago. Okay. So you have access to the slides, so you can do this if you would like. In a breakout room, you would work with your group to sort each pair of vectors into perpendicular, parallel, or neither. So if you click on this link, you can see that on the left side, there are 3 circles, perpendicular, parallel, neither, and then you would just drag this pair of vectors into whichever circle you think it fits into. And this is a way for you to practice thinking through it, and also a way for me to check for understanding. And you can divide the work up however you want if you're working with somebody. Okay, there are 9 pairs of vectors, so you could do, 3 sets of 9 or 3 sets of 3, or however you want to sort it out. Okay. All right, the last thing I want to teach today is the angle between two vectors. So this is a formula that's related to actually the law of cosines formula. So if you have two vectors that you're trying to find the angle between, this is the formula. So inverse cosine of their dot product divided by their magnitudes multiplied together. All right, so the formula looks a little harder than it is. You really just need to find 3 things. You need to find the dot product, both magnitudes, and then take the inverse cosine of this ratio of them. So I'm going to show you an example right here, and then you can try one. So angle between two vectors. So let's say we have vector C is 5, 7, vector D is -1, 4. How would you find the angle? Well, you need to find both magnitudes and you need to find the dot product, and then you apply this formula to them. So magnitude of vector C, we learned how to do magnitude last week, right? Distance formula or Pythagorean theorem, so square root of 74. Magnitude of D, again, Pythagorean theorem or distance formula, square root of 17. And then the dot product, which we just learned how to do today, 5 times -1 plus 7 times 4, which ends up being 23. And then our formula is inverse cosine of 23 over root 74 times root 17, which is approximately 49.574 degrees. All right, so with that, I invite you to try another one. Oh, this is a friendly reminder to put your calculator in degree mode for this, because you are finding an angle, not a radian measure. So go ahead and pause the video. You can go back to the slides if you want, or rewind to look at the example problem, and go ahead and try this problem. All right, I'm assuming you've tried it. Let's review. So magnitude of A should be root 53. Magnitude of B should be root 89. And inverse cosine, dot product is 46. So inverse cosine 46 over root 53 times root 89 is about 47.951 degrees. Okay. All right. So in class, if we had time, we do a little bit of workshop time where you could take a look at the homework. But this is a pre-recorded video, so you're just watching this to get caught up. All right, so some takeaways. So we have the dot product formula. We have the angle between two vectors formula and how we use the dot products and the magnitude to get that. And then two vectors that have a dot product of 0 are perpendicular. Vectors that are scalar multiples of each other are parallel. And we remember Arlo and Buster pulling the rope perpendicularly, and Arlo is doing all the horizontal work. Buster is doing all the vertical work. So that dot product is 0. All right. Email me for the CFU, please, if you didn't get a chance to do it. And I will, I thank you for watching, and I will see you next time. Have a great one.